we're familiar with the figure. It looks like this, but we never really got into and really anything more than just the empirical rule. So this formula, which is really a kind of a nasty looking formula, this actually is the equation of the curve, right? So that normal curve, that is y. If I put arrows on it like we would in an ordinary graph, I'd have that curve y. It is dependent on whatever the mean and standard deviation are for the population. So, in terms of typing that into a calculator, it's probably not the most advantageous use of time, because without knowing a mean or a standard deviation in particular, it doesn't really tell you much. But if you assume a mean of 0 and a standard deviation of 1, it simplifies down fairly substantially. So I'm going to say over here, assume mu is equal to 0 and sigma is equal to 1, in which case you get a much, much simpler equation to work with. You're still going to have a fraction, but everywhere that I have a sigma, that's just going to go to a 1. All right, so, and anywhere that obviously there's a mu, that's going to go to a 0. So this expression here within the parentheses, x minus mu over sigma, that's just going to simplify down to an x, right? Because x minus 0 is x divided by 1, still x, right? This sigma would become a 1 times root 2 pi would just be the square root of 2 pi. So you get a much, much cleaner equation, y equals e to the negative 1/2 x squared over radical 2 pi, right? This is the formula for what we call the standard normal curve, right? It's a standard normal curve, which we often abbreviate SNC. I mean, hopefully that makes sense. It's the first letter in each word. Typical way of abbreviating things, right? I'm not gonna make you graph the curve. I thought it'd be a good idea to at least talk about where a lot of the stuff we're about to do is coming from, right? So, and it's a little messy here, but again, that's E, Euler's number E, which is about 2.718, raised to the negative 1/2 x squared power all over radical 2 pi. And, like when you think about pi, you may think about trigonometry. E, also another what we call transcendental function, or associated with a transcendental function, just basically functions that transcend ordinary algebra, right? So, which, for a lot of people that's good. If you don't really love algebra, then knowing that you're dealing with something, I mean, the word transcend makes it sound like you're doing something like way more complicated than algebra. It's actually more simple because we could use numerical approaches like functions stored within the graphing calculator. All right, but let me just give you a quick look at what it would be like if we graphed it. All right, so not something you're going to need to do, but again, it's nice to actually see it in action. All right, so I'm going to hit OK on Grapher, add an element. We actually really haven't done much in this menu throughout the course. So, like if you have another math class that you're taking down the line and they allow the use of the numworks calculator, then, it'd be nice to see this stuff going in. All right, so I'm going to type in y equals basically this whole equation, but it doesn't quite fit one of my templates, right? We got all the different options here that I could modify. Unfortunately, the simplest one is the one that I'm kind of stuck with. So I can select that. It's like, okay, great. You saved me from having to type in the y and the equals. I still have to type in everything else, right? So I'd use my division to create a fraction. The E button, that's one of those buttons that, or functions that earned its way onto the main keypad. You don't have to go looking in a menu for it, right? That's how commonplace it is. So I would just hit this E to the power of X button, right? The one that's darkened in up there now. E to the power of X brings E. You would think it was E to the X power. It's e to any power. It allows you to type in whatever power you want. So I'm going to type in -1/2. Then I'll put in the X. The XNT key is what brings up the X. You could also, any letter that you want to access, you could get it by hitting alpha and then whatever the key is. It's kind of weird. I mean, I guess they're sort of limited in how they could express this stuff. So they chose on the keypad to put the capitals A, B, C, D, and so on. But if I hit alpha and then, for example, 2, it's going to bring up, so alpha 2 will bring up a lowercase x, even though it says that it would be an uppercase x. If you want uppercase, you'd hit shift alpha and then select it. But that's not relevant here. I mean, we dealt with that when we were working with the lists, when we need to bring in like a V1, value V1. We needed the capital V. Here we just want the lowercase x. All right, power of 2. Hit the down arrow a couple times. Pop in a radical 2. And again, pi is another one of those elements that earned its way onto the home screen. Or home screen, main keypad. So this is what I have in my equation on paper. Hit OK to lock it in. You can go to graph, have a look at the picture. Graph and calculators all have this one attribute that, you know, for better or for worse, it is what it is, where it decides on the viewing window, and it's not always the viewing window you want. So if you hit OK and you luck out and you have the perfect viewing window, that's great. We got lucky, but not always the case. So I'm going to go to graph. You could go to plot graph if you want, or just go right up to graph. And I kind of lucked out. I got a pretty nice view of the curve itself. It doesn't go all the way down to the x-axis, but I mean the heart of it is still there, so that's good. If you want to scroll down, you can navigate and scroll down a little bit. You could modify the axes. You know, so instead of going from -1.7 and change to +1.7, you might remember with the empirical rule, we went from -3 to 3 at least, right? Just because we're talking about going at least 3 standard deviations away from the mean. So you might modify this to go from -3 to 3. Confirm. And then for the values of y, I want to see the x-axis. I mean, not in an algebra course, so sometimes you're not really sure, okay, does this still follow the rules of what I would do in algebra? Is the horizontal still the x-axis? Is the vertical still the y-axis? The answer is yes. This is my x-axis. And I could extend this further if I wanted to, but negative values in the context of a normal curve don't have meaning, because negative values associated with a normal curve would correspond to negative probabilities. And probabilities have to exist between 0 and 1. So we really only focus on the top half of it. And it isn't until I draw my axis that I realize how symmetrical my drawing was. Not very nice, but kind of clean it up a schmidgy. I'm going to have to clean it up a whole lot more than a smidgy now. Hold on. All right, so that's my y equation. Yeah, I didn't really get much better, but I made myself feel better in the process, and that's also important. So I'm going to go on the low bound, something negative, something a little bit below, maybe like -0.1, and then above, something like 0.5. I only know that because when it first graphed, I saw that it crossed the x-axis around like 0.4-ish. So I like to give myself a little extra space on the high side. Then when you confirm it twice, it gives you a really, really nice looking picture. All right. So you could see that for particular values of x, you have probability values associated with it. I'm trying to get it to land right on the 0.1, the 1 even, but not quite. So I'm stuck on like 1.01. But it's giving us probability values associated with that location in the normal curve. All right. So we have probability distributions and probability density, right? So the probability distribution is really what you see in the graph. This is the distribution of all probabilities following a normal curve. All right. The area under the curve represents the density function. All right. So the area under the curve, I make a little note over here, total area under the curve is equal to 1, but areas under either the normal curve or the standard normal curve, it doesn't really matter because they both really accomplish the same thing, just different parameters. So the area under a normal curve areas are known as probability densities. All right. And both have meaning, both have value. It all depends on what you're looking at, though. In terms of whatever the question is, how it's phrased. Sometimes you're looking for the area at a particular location. Sometimes you're looking for the area over an interval. All right. Area at a particular location is not something you could really find. Right? Because if I were to say, at this one spot, what's the area? Well, and I can just kind of throw a value in here. Let's say I have this particular x value here at this location. If I were to say find the area, it's a one-dimensional figure. One-dimensional figures don't have area in that regard, right? So if I wanted to find the probabilities over an interval, what I'd be looking at is the area under the curve. But at a particular location, it would just be the point on the curve itself, assuming that there's no width, all right? It's all kind of theoretical. It's in a vacuum at this point, but we'll see some particular examples in a few minutes where it all, I think, will start coming together. All right. I did steal my own thunder a little bit, where down below I talk about the standard normal curve, the SNC. I mentioned that above. And again, the only reason I graphed the standard normal curve in the calculus because it's just going to be easier to do it that way. I could assume a mean of 0 and a standard deviation of 1 and just go from there. All right. Now what we're going to do is we're going to use the normal distribution to sort of level the playing field between different data sets. So the standard normal curve. So if I have a data set that has a mean of, let's say, 10 and a standard deviation of 5, and then another data set that's comparable, but the mean is like 12 and a standard deviation is 6, I can standardize so that they're both on the same curve. So that makes it an apples to apples comparison, right? In order to do that, I need to know z-scores. So I make mention of it down here, but I don't think I put a reminder of what the z-score formula is. So I'm just going to jot that in down here when I talk about z-scores. Z is equal to x minus, depends on if it's a population or a sample, but we're going to say population x minus mu over sigma. All right. So when I talk about a z-score, I'm talking about this formula or variations of this formula, as you'll see as we go forward. All right. This goes back to really the first unit. I put the recall statement in there. Prior to that, I say when you're finding the probability of z-score, you're looking for the area to the left of a z-score in the standard normal curve. That is kind of an oversimplification, but below that, and we'll get into the ins and outs of it, but below that I have the recall statement, and this meant a lot in the first unit. When we were looking for areas under the normal curve, we used the empirical rule, but we kind of did it the other way. where it was use the empirical rule to prove or demonstrate that the distribution you're working with is a normal distribution, right? So it wasn't really the case that we were saying, here is a normal distribution, now do math to it. All right, this is the reverse, or at least in the unit one, it was the reverse of that, where it was like, here's a distribution. Let's see if we could figure out if it's a normal distribution. All right, so we used the empirical rule to make that determination, but it was kind of like a circular logic sort of thing, where in order to use the empirical rule, or I should say, in order for the empirical rule to exist, it must come from some knowledge of a normal distribution. So if you know something's already a normal distribution, why are we trying to prove that it's a normal distribution? Right? The idea here was that this was vetted for a variety of different distributions, and this ended up being the hard, fast rule, which we can then apply to distributions that we're unfamiliar with. Right? Maybe it's bimodal or skewed distribution. Like, we could be given data that's in this form, or either of them, it really doesn't matter. If we wanted to determine if that follows a normal distribution, we would probably use a rule like this. But what we're going to do is assume that what we're working with is a normal distribution and use mathematical concepts that are stored into the calculator, which is a good thing, to figure out what those areas and probabilities would be, right? But what we can do is at least verify some of these. I just want to see if I fixed the typos from the last semester. I'm not sure that I did. I'll talk about that in a minute. But the standard normal curve, again, centered around 0, with standard deviations measured in increments of 1. Oh, this went a little off the rails. I didn't want it that big. So if I go from -1 to 1 in the standard normal curve, that should end up giving me about 0.68. All right. So that goes back to the empirical rule. About 68% of the data will lie within one standard deviation of the mean. So this area here, which I'll highlight in yellow, this corresponds to about 68% of the data, if it's a normal distribution. So about 68% of the data. But then it begs the question, okay, well, how could we discover that on our own? There's really two ways to do it. One is rooted in calculus based off of this formula. I'll show it real quick, just if anybody has background in calculus, you'll understand what I'm talking about. No offense to those of you who don't have background in calculus, but I'm going to just say it's not going to make a whole heck of a lot of sense what I'm about to do. But then I'll show you the built-in functions. All right. So if I wanted to find the area between -1 and 1 under this curve, if I've already created the graph, I'd go to calculate, and under find, there's a concept called an integral. Sorry, I don't know why that did that. All right. So you could select a lower bound, -1, an upper bound, +1, and it'll compute the area between those two verticals that I just really instantiated, I guess. So it's like, without getting into the concept of an integral, a calculus concept, this is basically a technique that you could use to find the area between particular x values that's captured between the x-axis and a curve. All right. So regardless of the shape of the curve, I could find the area contained between that curve and the x-axis, right? Just by using this integral function. But you can see the notation there. It's kind of crazy looking. If you don't, this is what I was talking about. If you don't have any experience with calculus, then you're looking at this and you're like, I don't even know. Is that musical notes? What's going on here? But the concept, not really the concept, just the visual, the representation, it's pretty clear what we're finding. We're finding the space under the curve, and above the x-axis, bounded on either side. All right. Now, fortunately, and it's not just the NumWorks calculator, but really any developer who I wouldn't even say builds calculators. Calculators built, they just do the programming. Most calculators have this functionality built into it. All right. It's just coded into it as an application. All right. So we'll go back to, well, there's actually 3 ways you could do this in the calculator. I tend to default to the calculation menu and the toolbox and all that. So you know what, I'll just do that. And I'll show you a third way. But if you want to tune me out when I show the third way because you're like, listen, I got it after the second way, then that's perfectly fine. I will say you're probably not going to want to do it the way I just showed you, but that's more to tie this to the calculus. All right, so I always have this thought in my mind whenever I teach this class. For some people, this is the beginning of their math journey, and other people, this is the very last class they got to take before they're done. So I don't know where everybody is. Some people, like you just came from a Calc 2 class, and you're seeing areas under a curve, and you're like, how does this connect to that? I like to show that too. All right, so it's just a little something for you. All right, but let me go into the calculation menu and show you the shortcuts. Now, this shortcut, or the set of shortcuts that I'm going to show you, only apply to probability density functions. All right, so if you wanted to graph a parabola and find the area under that curve, you're not going to use what I'm about to show you. You'd actually use what I just showed you, but that's, again, more for a calculus course. All right. So, toolbox. I mean, we're kind of living in the toolbox, so that should be easy enough. I'll jot it down here. Toolbox. Probability. Distributions. All right, so we've lived in the probability menu. We've gone to probability and we've done the combinatorics, you know, the factorials, the permutations, all that stuff. We're going to distributions. Select normal. And then once you do that, you have a few different options to work with. Actually, 4 different options. The first 2, norm CDF and norm CDF range, are ones that'll give you areas under the normal curve. All right. So here it's norm CDF or norm CDF. Let me just zoom this in, sorry. Norm CDF range. All right. Both of them will finds area under the normal curve. All right. Normal curve, so it'll work with any normal curve. So meaning the mean and standard deviation are anything, or the standard normal curve where the mean and standard deviation are 0 and 1 respectively. All right. That's why it asks for the parameters. So anytime, I don't want to get too computer sciencey here, but anytime you have some sort of method that you're using in the computer science realm, like if you're calling a method, that method can be an overloaded method which has multiple parameters, or it could just be a default method that if I were to click on, if it didn't have stuff in the parentheses and I clicked on this option, it would just do something. It would produce an answer regardless of what the parameters are. But here it's saying you want to put in an A value, a mu, and a sigma, right? They give you a little notation there. You see that it says P of X less than or equal to A, right? That's the calculator's way of saying that what this is going to return is the area to the left of whatever the A value is, all right? Whereas the second one is going to return the area between whatever you call the A and B values, all right? So this is for area to the left specifically, and this one is area between, all right? So I'll make a little note. Area to the left of A, put A in quotes, And this one is the area between A and B. All right. So area to the left of whatever you're putting in for A, and the area between whatever the A and B values are. All right. Now the inverse norm, we'll get to that in a little bit. Baby steps here. But that goes the other way. If you know the area, it'll tell you a particular z-score. All right. So when I reference the A and the B values, they're talking about z-scores. It's kind of probably a little annoying, I guess. Why can't you just say z-score instead of A? I don't know. My guess is because they want to use the same parameters for multiple different functions, and the different functions don't all involve a z-score. They'd rather just keep it A and B. But yeah, it's one of those things where you just kind of make a note to yourself that when you see the A and B, you're talking z-scores. All right. But let me just show you this in action real quick, because I have this statement down here that says the probability that a z-score is between -1 and 1 is 0.68. It's not exactly 0.68. It's approximately 0.68. But if I let this entry here, that -1, be my A value, and this entry here, that's going to be my B value. As long as I know the mean and standard deviation, and for a standard normal curve, it's 0 and 1, right? Standard normal curve right here. So it's written above, but that means mu is equal to 0, sigma, all right, poor quality sigma, got caught between a theta and a sigma. Sigma is equal to 1, all right? So what I would do in my calculator, because I have an A and a B values, I'd select norm CDF range. Puts the commas in for you, which is nice. If you accidentally delete one of the commas, it's also something that earned its way onto the main keypad. See the little comma there? It's got its own key, so you could bring it back. You don't have to, like if you accidentally delete a comma, I've seen this happen before, even with the TIs. I'll have people like wipe out their entire line of everything they just typed in. Be like, well, I guess I can't get the comma back unless I do it all over again. You don't have to. Just look on the keypad. Odds are it's there. All right. So I'm going to put in a -1. Oh no, I accidentally deleted my comma. Oh, comma, +1, the mean of 0, standard deviation of 1. All right. You can close the parentheses or not. Since there's nothing following this, if I hit OK or enter, calculator is going to automatically assume I want to close the parentheses on the method. So there you go, 0.6826 and so on. So it's not exactly 0.68, it's approximately 0.68, but this is kind of a demonstration, I guess, of where we got that 68% to begin with. Right, but it is very much chicken or the egg kind of deal, because we got the 68, 95, 99.7 percentages from studying the normal curve, the standard normal curve. But how did we get the standard normal curve equation to begin with unless we had an idea of what those percentages were? So really what happens is, and this is really not just limited to statistics, but math in general, is you have an idea based off of trials of what should be happening, and you manufacture a function to coincide with what is actually happening in reality, right? So normal curve works its way into all aspects of the universe. Right? It's just one of those things that, like pi and e, they're naturally occurring constants, right? Gravity can be thought of as one of them, but depending on where you are, gravity, the acceleration due to gravity changes. But exponential rate of growth, pi as really 2 pi, the number of radians in the circumference of a circle, those are constants that never change no matter where you go. Right? You go to a different planet, it's still the same. All right. So that was built, or at least this normal curve was built off of the fact that in daily observations or even just scientific inquiry, it was really just noticed that, yeah, about 68% fall within one standard deviation, about 95 within two, and 99.7 within three. Let me see if I could build a function that will capture precisely that amount of area. And then we'll use that to kind of backtrack and investigate other things that are just one or two standard deviations away from the mean. They had a really cool thing. The Science Museum in Queens, I forget the name. I think it's just called the Science Museum. But anyway, they have this big normal distribution. Like it's a pegboard. It's kind of like a Plinko board. So it's got little studs in it. You know what the good example is when you go to the amusement park and you have that game where you drop the disc and it bounces off the little studs that are there, and it eventually falls in a slot. If you fall into a good slot, you get a nice prize. If not, you just spent $5 on nothing. You know, that is an example of a normal distribution because or at least a distribution. But the way they designed the one at the Science Museum was so that it would follow a normal distribution. So they put the pegs in at appropriate locations, and they would just drop marbles like throughout the day. They'd have like kind of an unlimited supply of marbles, and they would just drop them in there, and you'd see as you walk by, oh, more and more are falling in. And then once it formed a normal distribution and they ran out of marbles, they dumped the whole thing and do it again. And every time they dropped the marbles, it always formed a normal distribution. Right? If you think about it, like, and this is a classic calculus example, but I guess you could kind of visualize it. If you were to take like a big thing of Morton salt and just start slowly pouring it onto a table, it's going to create a bigger mound in the middle, and then it's going to kind of feather out as you go. It's three-dimensional, so it looks like a cone, you know, like or an anthill or something like that. Even anthills, that's a good example. But it's really forming a normal distribution because the cross sections of that figure, that three-dimensional figure, will look like that. All right, so it's something that occurs naturally, but you know, like the term bell curve has gotten such a negative connotation in the past, you know, because it seems like it's almost always used to categorize people, and that's anytime you categorize people in any way, it just doesn't feel right. So it becomes a kind of a tricky thing as sort of a buzz term. But I've seen examples of people using the concept of a normal distribution in sort of, let's say, nefarious ways. Like the classic example from college is the business school where I went. They graded on a bell curve. So they called it a bell curve because they didn't want to use the term normal distribution because it technically wouldn't have been correct. But what they would do is based off percentages. If you have 100 students in a class, 68 of those students would be within one standard deviation of whatever the class mean was. All right. And so they would assign it. I'll do it on this diagram here. And it honestly, it doesn't really feel good if you're in this kind of situation. And a lot of places still do it. Mostly business schools are the most guilty of it. But this is your C range. All right. So anybody who falls in this category is a C. You know, maybe a C minus, a C plus. All right. Then you have your B range, like same deal, B minus, B plus. We don't do minuses in this school if anybody's not familiar. Then you have your A range, and you have your D range, and then everything after that to the left would be your F range. All right. So right in the middle, if you're average, they define that as a C, so you get a C for the course. All right. So if I tell you that throughout the course, a student had the class of students. And so you have 100 students, and the class average at the end of the course was a 95 with a standard deviation of 1. I'm kind of going over the top here just to prove the point. That would make this, if the standard deviation is 1, this would be 94, 93, 92, 96, 97, 98. And what they would do is they'd say, well, we're following the normal distribution, or the bell curve, they would say. these are the only people who get an A in the course. These are the only people that get Bs. Depending on where you are in that spectrum, you get a minus or a plus. These are the only people that get Cs. If you look all the way to the left, you see that you got a 92, you failed the course. Like, have you ever gotten a 92 on an exam and thought, man, I bombed that one? It's different from, I thought I did better than that. I thought I was going to get a 100 and I only got a 92. But you didn't think, well, there goes the semester, I got a 92. But I know the Stern School of Business, they used to do that. I don't know if they still do it, but that's pretty horrific. Now, they called it a bell curve because it was not a normal distribution. I guess I could leave that there. It's fine. When you have a distribution of scores, it's more like this. All right. So they called it a bell curve because this part of it looked like a bell. Not because it was a perfect normal distribution, but all of these values here. So middle, 1, 2, 3, 1, 2, 3. This is the realm of really just anything that was worth talking about, I guess. All right. So if you got less than, so it would be 2 standard deviations below the mean. So I put that in the wrong spot. If you got less than this, you get an F. All right, but that's a way bigger interval than the individuals over here who would get the A's. All right, so actually over here that would get the A's. So they weren't allowing anything really beyond the usual interval. If you remember from the first unit, any value that falls within 2 standard deviations of the mean is a usual value. Anything beyond 2 standard deviations, we actually did this in the second unit too, would be considered unusual. So if your score was unusual on the low side, you failed. If it was unusual on the high side, well, that's not possible. Or at least that's their mentality. No, it was possible. More than 3 standard deviations. So they wouldn't allow for outliers, but they would allow for anything unusual on the high side. Oh, you did unusually well. You get an A. You did unusually poorly, you get an F. And so when you frame it that way to people, it's like, oh, that makes sense. Unusually high, yeah, I should get an A. Unusually low, that's probably not a good thing. Maybe I don't want to fail a course over it, but I can see the justification for that. But those C individuals, they were locked in. You're middle of the road, you're C, even if the middle of the road is a 98. All right? So that's how this stuff can be, I would say, perverted, not in the gross way, but like in the technical definition of that, where it's just you're taking something and veering it off of what it ought to be for a negative reason. All right. So, yeah, that's an example of how it could be used. And one of the things that coming out of this class, hopefully, that you'll get is the ability to see through other people's bull. All right. So when they throw statistics, everybody throws statistics around these days. Somebody's going to throw a statistic at you, at least you can call BS on them. All right. So we're going to start with some more basic examples, something less depressing, I guess. So the examples here, assume the mean is 0 and the standard deviation is 1. That's not always the case. It's just because we're talking about a standard normal curve. Oh, no, it's all good. You're welcome. So, because it's a standard normal distribution, we assume the mean is 0 and the standard deviation is 1. But I'll show you some examples later on where that's not necessarily the case. We want to find, see, this is, I knew I didn't fix it, the numworks. And the process is on the previous page, so that part should be okay. When I find the probability that Z is between 0 and 1.5, I think personally, I think it helps to think of the notation because the notation aligns with what's in the calculator in terms of the built-in function. So if you write it the right way, it just makes it easier to put it into the calculator the right way. So what this is saying is the probability that z is between 0 and 1.5. All right, probability z is between 0 and 1.5. Now, on the normal curve graph, 0's in the middle. We're counting out in increments of 1. So I'll label it up here, but you don't always, oh, that's not a 2. You don't always have to label every part of the graph. Just the relevant parts are really all you need, right? Because the scale is established based on the fact that it's standard normal curve. So 0 is right in the middle, 1.5 is right about, yeah. So what I'm looking for is this area. All right. The diagram, it's important. Maybe not as important as statistics teachers like to believe it is. And so, like it's kind of a tough sell sometimes to tell you, listen, I need you to draw the diagram along with the statement, right? To get full credit. If it's not a multiple choice question, when you show your work, that's part of the work, all right? There is a good reason for it that we're really not going to see until we get a little bit further into the unit. So for now, I'll just say, draw the diagram. Trust me, it's important, all right? And then later on, you can come back to me and say, you know what, yeah, you were full of it. It wasn't as important as you said it was. So I regret having drawn all those diagrams. One thing I will say is for a test, if I ask you to draw if I ask you to do a problem like this, you'll need to draw the diagram. I'll give you the framework of it though. So I'll give you this, and you just have to mark it up. All right. So that's my compromise there. All right. One valuable reason for why one might consider drawing the diagram, even if if it wasn't a requirement, is to get an idea of what you're looking for. If the total area under the curve is equal to 1, and you just shaded less than half of that, and then you type it into your calculator and come up with 0.75, you know you did something wrong, right? So there's that one little payoff, at least in the early going, right? It's going to be norm CDF range, so same function, but you see how, again, I wish the pointer went to different apps, but you can see in gray there, A is less than or equal, they say X, we say Z. A is less than or equal to X, which is less than or equal to B, has the same structure as what I just wrote down on paper. So when I go to my calculator, I know that this is going in for A and this is going in for B in the norm CDF range. All right. And something to be mindful of, if you write norm CDF range on the test paper when the time comes, that's fine. You're not really talking statistics at that point. You're talking about, stuff that you typed into a calculator, right? And, it's not often in this class, but there are a couple of students that prefer the TI calculators, in which case the syntax is completely different. So if you write norm CDF range, I'm even thinking going forward, like let's say that you're taking this as a prereq, you're going to a 4-year school and you have to take a follow-on statistics course, you're going to write this and you're going to be like, what the hell, what is that? That's okay, norm CDF range, good for you. It's this that they care about. Like recognizing that you're asked to find a probability, and then the diagram corresponds with that probability statement and the answer corresponds with both. All right, writing 0, 1.5, 0, 1, that's great. It's fine. I mean, in the long run, it's okay for this class. I mean, I guess it's useful if I'm grading your paper. And it's like, oh, I see, you put the 1.5 where the 0 is supposed to be. But aside from that, it's not really demonstrating knowledge of statistics. It's demonstrating knowledge of numworks. right, which is not the name of the course, but, it's a more philosophical thing. Practically speaking, most of you are going to write that down and put an answer. You're going to write this down. You're going to write that down. You'll throw that in there and you'll get the answer and everybody's happy. But just in the long run. So about 0.433 would be your area under the curve. Right? Which, does it look like I shaded exactly 43.3% of the curve? I have no idea. I know I shaded less than half, so I should have gotten an answer that's less than 0.5, right? I shaded a good amount of it, so I wouldn't expect it to be like 0.2 or anything like that. I expect it to be somewhere in the neighborhood of 0.5, but below it. 0.433 fits that, so we're pretty comfortable with this. Now, number 2, z is greater than -3. So again, you can just plot the relevant part of the graph. I'm going to do the whole thing, but if you just wanted to do, like, label the -3 and the 0 and then do your shading, that's fine. I just feel like it looks weird, so. But then again, you're taking a test and you're running out of time and you're like, you don't want to waste time on like little details that don't matter for anything. Of course, you skip the irrelevant stuff. Now, what this is telling me to do is shade to the right of -3. So this is a probability statement. Z is greater than -3, which is all the area to the right of -3. All right, so that's damn near all of it. You can't really tell based off the quality of the diagram, but there is that little bit of area. If you go beyond the -3, it doesn't actually touch the x-axis. It just looks like it based off of the pixels. I mean, when you really zoom in, you can see the pixels. But there is still a little bit of area that's not accounted for by my shading. So I don't expect to get exactly 1. The only way I would get exactly 1 would be if I went from -infinity to infinity. But these calculators are not infinite, they're finite. So they run out of capacity to go out further, like the processor, the storage, memory, all that good stuff. It only goes so far, right? So that's why sometimes when you do a probability question, it'll say the probability is equal to 1. It's not really equal to 1. It's 0.9999999999999. But it only has the tolerance to go out 8 decimal places. So after you get to beyond the 8th one, it's like, all right, well, I got to stop here. My programming is limiting me to stop after the 8th decimal place. Well, I got to follow the rules of math, so that last 9 is going to force the prior 9 and the prior 9 all the way up and force everything up to 1. Even though it's 0.999999999, the calculator thinks it's 1. So in instances like this, it may return a 1, but it's not really a 1. Just like if I went the other way, to the left of -3, it might give me a 0, but it's not really 0. All right, so we got to be careful about little things like that. Right? But typing this in is a little tricky because my first function here is area to the left. Right? You see how it says probability x is less than or equal to a? Well, I want to go the other way. If the total area under the curve is equal to 1, you can use the complement rule, and that is 1 minus the probability of everything we don't want. All right? So probability that z is less than or equal to 3, in which case my a value becomes the -3. I'll show you a different way in a minute that you might like more. But this is the, I guess, mathematically most efficient way to do it, I suppose. Actually, I would say computationally, not even mathematically. The most efficient way to do it would be to use calculus, but that's not the case. So I could use my norm CDF, put it in the -3, 0 and 1 for the mean and standard deviation. Now, if I just hit enter on this, it's going to give me area to the left of that -3. You may be curious. So let me hit OK. Gives me that decimal. All right. That's the area that I have here in red. All right. That's exactly what I don't want. So 1 minus that answer, you just use answer at this point, will give you the area that you do want. All right. So about 0.99, well, 999 if I round to 3. So it's 99.9% about. A lot of folks prefer to go with the norm CDF range method, though. And it's like, well, how do I do a range if I don't have two different bounds? All right. So I'll show you real quick. I'm just going to write down what I typed in the calculator here just so you have it. But so you could do 1 minus norm CDF. We did -3, 0, 1. Or you could do a norm CDF range. Now that norm CDF range, that could be kind of conceptually tricky, but the procedure isn't bad. It's just understanding why we could do it this way may be a little dicey. But if you think about where we're starting our shaded region, we're starting it at -3, and we're never stopping. If I'm going to be greater than -3, I could be any value greater than -3. I could be 100,000. I could be a bazillion. Technically, in a purely mathematical sense, I could get to infinity. So when I'm looking for the probability that z is greater than -3, I'm looking at the probability that z is between -3 and infinity. So my A value would be -3. My B value would be infinity. The problem with that is there is no infinity button on the calculator. And you're not going to find an infinity button on calculators that are actually purely infinity. Because if you can't get there, how can you quantify it? All right, calculators are finite. So even if there was a calculator out there that had an infinity button, it wouldn't actually be infinity. It would be just a number that's so large that you would not be able to distinguish it from infinity, like you as a person. All right. So what we can do is that. Choose a number that's so large that the calculator or other people can't distinguish it from infinity. Now, in the case of a normal curve, very large isn't really that large. Like 10 will do the trick, right? Because if you think about the y values associated with any of these x values, you never want to lose sight of that. These are x values and these are y values, and any point would have coordinate. This would be 1 comma about 0.3-ish, right? But if I get out to 3, I had a number that's so small that my curve and my x-axis appear to merge, even though they don't actually merge. There's still some space there. It's an asymptote. But it's so close that it's indistinguishable to the eye. So imagine if I go out even further, which is really why we stop the curve at 3, because it appears to merge. The curve appears to merge with the x-axis at 3. So is it going to merge any less or more to the eye, to the naked eye, when I get out to 4, 5, 6, 7? It's containing such a minuscule amount of area that it's indistinguishable, right? So we're not really going to gain much more by going out to 10 than we would if we were to go out to 9. Or if I went out to 100,000 as opposed to going out to 10, right? So what I say here is I go from -3 to something big, very technical mathematical term there, big, 0, 1. And the question I always get is, how big is big enough? Well, try something. So -3, I said 10. That's not a -3. -3. What? I must have hit an alpha here. Is that what's going on? Yeah, there we go. -3, I'll put it in a 10, and the 0, the 1. lock it in, I get that decimal, which happens to be the exact same decimal I got when I used the norm CDF function. So I'm pretty confident I went out far enough. But if you're not sure, like you have a moment where you're like, oh wait, did he say 10 was big enough or not big enough? I'm not really sure. Go out something a little bigger. If the decimal doesn't change, then you've gone as far as the calculator is going to let you go. All right. And so, I mean, if you want to, you can kind of play around with, all right, what's the least I can go out and still get that same decimal? 5 wouldn't be enough. But you could see, if we're just rounding to 3 significant digits, 5 kind of is enough because this is still giving me the 0.999. It's only for the latter values where it starts to kind of fall off a little bit. Right? So then maybe you try 6. Close. It's only off by that 1 decimal at the end. I mean, if you want to go nuts, you could go to like 6.1, 6.001. You'll find the value that'll make it land on it perfectly. But 7 will probably be enough. And it really doesn't matter what you choose as long as you get the appropriate decimal value. All right. So that's something that I'll tell you, I teach the same concept actually within the last week and a half in my high school class. And it's kind of a mixed bag where half the students are like, well, I'll just use that norm CDF thing. That's fine. I'll just do that. And then the other half of the class is like, you know what? I'm going to use norm CDF range because I don't have to worry about thinking too much. Because I just use the same function over and over again. I don't have to add that extra layer of deciding which function makes more sense. Do I use CDF? Do I use CDF range? I don't know. I'll just use CDF range. I'll just play around with the numbers and it'll be good. All right. But as I just showed you, going big doesn't really mean that you have to go that big. I mean, I had the 7 here. If I did 7,000, I mean, what do they gain? Nothing in terms of visible decimal values. Now, for the 700th decimal place, there will be a little bit of a difference, but I'm only going out 3 significants, so who cares? All right. Now, we do have to kind of address as we go forward the difference in how a greater than is treated compared to a greater than or equal. It's not really relevant in this instance, though, because what we're looking at is when I say area to the right of -3, or if I were to actually include -3, if I say greater than -3 or greater than or equal to -3, it really just amounts to the same thing because that vertical line that we draw at -3, it doesn't have any width. All right, so if I fill the area, even this one, for example, if I fill the area between 0 and 1.5, the area goes up to the boundary of 0 and up to the boundary of 1.5. Whether I'm saying I'm including that boundary or not is irrelevant because the boundary itself doesn't have any thickness. It's just a barrier. All right? You tend to think like, oh, well, what about the barrier itself? Well, the barrier is just an end point or an end line on that interval. If I were thinking of it as a pool, like a swimming pool, and I fill it with water, I don't know that in terms of the volume of the water, I don't know that I care about how thick the walls of the pool are. I just care about the water going up to and making contact with that barrier. But the thickness of the barrier itself is irrelevant. Right? Now, structurally speaking, you want to have thick enough walls to accommodate the amount of water that you have in the pool. That's a physical thing. But in terms of the pure mathematics of it, the boundary compared to the area, the boundary does not have any significant meaning except to cordon off the relevant area. Long story short, that means we treat greater than and greater than or equal exactly the same. We treat less than or equal exactly the same. All right. So when I say area to the left, area to the right, area as at most, all right? So I'll look at numbers 3 and 5 here. This is saying the probability that Z is less than 1.28. This one is saying the probability Z is less than or equal to 1.28. Spoiler, I'm going to do the exact same work for number 3 and 5. All right. And in fact, I'm going to do the work for number 3, and then I'm going to copy paste it to number 5 because they're asking for the exact same thing. All right. You do have to kind of ballpark where the 1.28 is. As long as you put it somewhere between 1 and 2, you don't have to worry about losing credit or anything like that. Just maybe don't do it exactly halfway between 1 and 2. It's just a thought. Sorry, it's locked into a non-vertical. Yeah, close enough. All right, so I'm looking for this area here. Now, area to the left is probably one of the easier ones to do, I would say, because you have that built-in function, right? But the thing is, and this is why I was talking about the difference between less than and less than or equal, is because the calculator has a less than or equal to symbol built into it. So then when you write this and you have a less than, I didn't want you looking at it being like, oh, wait, there's got to be a different function. I have a less than, but that has a less than or equal. I can't use this. What I'm saying is, regardless of less than or equal, we're still using the same function. All right. So I'm going to select that bad boy, norm CDF, norm CDF, not the range though. 1.28, 0, 1. Lock it in. Now I drew my diagram, and my diagram shows that I've shaded more than half of the available area. Total area under the curve is equal to 1. I have less than that, but more than half. So I'm looking for something in, I mean, if I had to guess, probably in the 0.7s, something like that, but I don't know. Let's see. Not even close, 0.9-ish.
We don't use a minus or plus 1?
You would use the 1 minus if you want an area to the right. So since this is area to the left, you could go straight for the norm CDF.
Okay.
All right, so this is, if I round to 3 significant digits, this is going to give me about 0.900. All right, so I knew it was going to be between 0.5 and 1. The way the diagram was drawn, it kind of felt like it'd be around 0.75, 0.8. It's 0.9, but it's not different enough for me to doubt whether I did the process right. It's different enough for me to question whether I understand correctly how much area is in each particular region. But because it's a normal curve, you have the highest values in terms of the height closer to 0, so that's going to capture more area. So it really just depends on how much is in this region. But also you could think of it as, if you know that about 68% is in this interval, and then, like another 16 over here, that gets you in the neighborhood of 0.8. So you have an idea, but really as long as you can come up with an answer that's consistent with your diagram, generally, then you're fine. All right. Now, area to the right, and like I said, I'm just going to take that work and copy it down there. I'll do that in a minute. But area to the right, probability that Z is greater than 1.00, I'm just going to say 1, as opposed to number 6 where it says Z is at least, so probability that Z is greater than or equal to 1. Again, same question. Posed a little bit differently, but same idea. All right. And again, you draw your curve. Well, you have your curve. Label it up. So put the numbers in. Mark it off appropriately. Shade appropriately. I'm going to make a vertical line at 1. And then it did that on me, which is weird. Hang on. To the right of, that's all this area over here. So here I would do either 1 minus norm CDF, 1, 0, 1. And again, repeat this a few times just so it kind of becomes second nature. 0 and 1 in each case, whether it's norm CDF range, the last two parameters are 0 and 1, because that's what the mean and standard deviation are for the standard normal curve.
I'm sorry, can you say it one more time?
So the last two values represent the mu and the sigma in the formula. In the standard normal curve, the mu and sigma are 0 and 1 always. So that's why each one of these commands ends with a 0, 1. So 1 minus norm CDF 101, lock it in, and it says that I should have about 16%. Now this would round to 0.159, so 0.159. Now, based on the empirical rule, that should make sense, right? Because within one standard deviation of the mean, you have about 68% of the data. So if I start at the mean and go up, only up one standard deviation, it should be half of that. So instead of 68 between, it would be 34% here, right? This side here, from 0 all the way down to negative infinity, that's half of the graph. That's 50%. 50% plus 34%, 84%. What's left over, about 16%. All right, so it's pretty consistent. But again, you just need to look at your answer and say, okay, that's possible based off what I've drawn. All right, I shaded less than half the graph. I should get an answer that's less than 0.5. All right, it's the between stuff that can be dicey because, you know, like if you have, I'll just use this space here. But if I have like an area going from here to here, then I really don't know what I'm looking at. It could be 30%. It could be 100%, not 100%. It could be like 50%. I have no idea. All right. But if it's all contained on one side, it's a little easier to pull. So like I said, a quick copy paste. Oops, I think I might have got what I need there. Copy. Yeah, look at that. I should be mindful of the fact that you all can't copy paste before I say something like, look how easy that was, as you're scurrying to draw it all in. But yeah, conceptually, that's the idea. Now, again, for numbers 4 and 6, I could have done norm CDF range. I would start it off at 1 and then just go to some big value. So if I did that norm CDF range, 1 to something big, 10 should be good enough. 0, 1 gives me the same decimal, so I'm pretty confident. And again, that high bound, I said 10, maybe you go 15, maybe you go 20. If you're not sure you've gone far enough, do the computation, get a decimal, then do the computation again with a bigger number and see if there's any change in the decimal. If there is no change, then you've gone far enough. All right, so I'm not confident about this, so I'll change my 10 to a 100. No change in decimal. I could have changed it to a 10.1 if I wanted to. Didn't matter. As long as I went a little bit bigger or a lot of bit bigger, just bigger, no change in decimal, I'm good. And even if there is a change, I mentioned this before, even if there is a change in decimal, but it won't impact your rounded answer, then you've gone far enough, right? So again, who cares if these last 4 decimal points change as long as you're going to round to the same number? No matter what I have along the lines here, it's going to go 159 regardless. All right. So the last thing we're going to do is learn how to go the other way, which really, I mean, it's not terrible. One good thing about it is you're limited to just one command. It's the inverse norm function, right? Inverse, I mean, if we just tend to think of inverse as doing the opposite of the thing that it's referencing, then that's really probably a good way to think about it. And that applies beyond statistics. It could be anything. You know, if I have an inverse trig function, like you have a trig function, Now you're working with that trig function in reverse, changing the variables. All right, but here, again, I have the notation wrong. This is related to the Desmos calculator, which apparently is going into production, but we're not there yet. All right, so it's going to be, I'll just jot it down here. Toolbox, probability, distributions, normal, and then the one that you want is the one that says inv norm. All right. So that inverse norm function takes in area to the left of some z-score and returns the z-score. All right. I know, weird phrasing, but what came to mind first. So takes in the area to the left of some z-score. That we don't know what the z-score is, but we do know the area corresponding to it. Now there's a whole world of questions about, like, okay, how do you know the area but not know the z-score itself? We'll get to that. But it'll give you the z-score that corresponds to a given area, but specifically area to the left. So if a question's asking you about area to the right, you have to make a numerical adjustment in order for this function to work. So you see that there is an inverse norm, an inv norm, but there is no inv norm range. All right, so we're limited to just this one function. Then you have the norm PDF. That's conversation for a different day, but that just really, all that does is it gives you the point on the curve corresponding with a particular z-score. So there's room for discussion on that. It just doesn't really tie in nicely with what we're doing today, right, or this evening. So I put the recall statement in there, the percentile rank, right? Percentile ranks coming out of nowhere, is the percent of scores below, or in this case, to the left of a certain score, right? So if you know parameters of a particular distribution, like you know that the mean of the distribution is a 100 and the standard deviation is 10, like an IQ test, or what the IQ test was back in like the 80s when I first learned about IQ tests. You might be concerned with, okay, well, what score would I have to get to be in the top 90th percentile, or to be in the 90th percentile? Have you ever gotten one of those standardized tests, like back when you were younger? Like they do it I feel like they do it every year now. Back in the day, it was like you did it in 4th grade, you did it in 8th grade, and then the next time you did it was like the SATs or something. Now it's like, oh, we have standardized testing. Wait, again, this year too? 1st grade, 2nd grade, all the way up. It's like you can't even read correctly in 1st grade, and they still have you doing a standardized test. But you get the report back, and it says that you're in the 99th percentile. It's like, what does that mean? Well, it doesn't mean you got a 99 on the test. But, like you talk to a 2nd grader, they're like, I got a 99. Dang it, I almost got a 100. Like you could kind of see how they would interpret it that way. A percentile rank is the percent of individuals that you beat in that process, or that you're better than. Now, depending on the context, a high number might not be a good thing. Like the 99th percentile, if talking about golf scores, would actually be a very low number, right? Because the fewer the strokes when you're playing golf, the better you're doing. Like if it takes you 10 strokes to get the ball in the hole and it only takes me 2, I did a better job than you did, right? So lower number is better, whereas if you're playing basketball, the higher number is better, the more points you get, right? So there is that part of it, the interpretation, which we'll get to. But for now, if we just assume we're talking about like a standardized test, if I'm in the 99th percentile, then that means I beat 99% of the people who took the same test. which I would argue is actually better than getting a 99 on the test. Like I got 99% of the questions right on the test. That's great. I beat 99% of the population. I think I like that a little bit better. All right. So it's like the students who, you remember this maybe from high school. It's like they got their test back and they wanted to know what you got on your test. I'm like, oh, you care. But then you saw their reaction when they did better than you or when you did better than them. And you're like, oh, you didn't care. You just wanted to know if you beat me. You didn't, but, like we can all dream. So here I'm saying find the z-score, not an actual score, but the z-score that represents the 90th percentile. So just going back to the first unit, when I talked about z-scores, it was a way of standardizing data. So if I'm in a class where I just took a test and the class average was an 80 and the standard deviation was a 5, and I got a 90 on that test, I'm right at the borderline of what is unusually high, which is a good thing for me. All right. Now, if I'm comparing that to a student who got a 92 on their test in another class, I got a 90, they get a 92, you'd say, well, you did better than me. But then when you find out their class average was a 90 and the standard deviation was 5, they're not even one standard deviation above the mean. They're average. I'm special. They're average. All right. Unusual in that context is a good thing. All right. Being in the usual interval, not so much. If I want to find out, so let's say I'm the one that's designing the test, and I know that I want the class average to be this and that, and I want the A grade to be the 90th percentile or better, so not getting 90% of the questions right, but beating 90% of the population, like that Stern School of Business example I gave earlier, then I could use a method like this. All right. It allows us to create benchmarks, cutoffs for different grades. Now, grades could represent actual grades, but it could also mean different levels of achievement in some capacity. Like number of people that get promoted to middle management, to upper management, like things like that. So there's all the possibilities, salaries for crying out loud, tax brackets. Like, how do they decide on tax brackets? Like, why is $320,000 for a married couple? Why is that the benchmark for the uppermost tax bracket? You follow probability methods like this. You could say, well, that accounts for the top 5% of the population, and we only want to tax 5% of the population at the highest possible level. They work backwards from what they desire to happen, find that benchmark, and then convert it over into a dollar amount, and now you have that cutoff of $320,000, which seems to come out of nowhere. But that's the justification for it. All right, so here, I know 90% is going to be somewhere, and you're forgiven if you don't label the graph the way we did on the previous one, because I don't know if it's going to be between 0 and 1 or 1 and 2 and so on. I'm just going to take a stab at it. This looks like 90%. I don't know. You might say this looks like 90%. You're not wrong. All right, so you can put it anywhere you want. Shade to the left. That's about 90%, so I'm going to say 0.9. So in this context, we're looking for the z value that gives a result of 0.9. All right. So what I would say here, I don't see many happy faces typically when I write this notation, so just forgive me, but z less than z sub 0. All right. So this z here corresponds to any possible z-score. Could even make it, you could say all possible z-scores. This one, less than, so in this case we're saying below. So any possible z-score below the benchmark z-score. All right. You know, to oversimplify the terminology, which may be useful in this case, that first Z represents the shaded area. That Z sub 0 is a particular Z value that represents the cutoff between the shaded and not shaded area. All right. This allows for really infinitely many Z's to satisfy this inequality, right? Because if the Z value that I'm referencing here is a -2, yeah, it falls in the shaded region. It's over here. Actually over here. -3, -10, -0.1. All those different possibilities are counted for. Any possible Z-score below whatever the benchmark Z-score is. So that's the proper notation. How it boils down in the calculator is actually much simpler. Inverse norm. So I'll make a little note. This is my Z sub 0. Inverse norm follows that notation. You can kind of see it. I mean, again, it's so far away and it's like so tiny and grayed out. But when it says x less than or equal to m, it's following that same structure here. We're just using Z and Z sub 0. The A actually represents area in this context, which is nice for this method, but for the norm CDF, the A and the B values mean something completely different. So it's a nothing's perfect kind of situation, right? But the area to the left is 0.9. The 0 and 1 constitute the mean and standard deviation. So this is what I would put in. All right. And it's going to give us a Z-score. In this case, 1.28. Probably could have. Actually, I plotted it right around the right place. But I forgot that on the previous page, we found the area to the left of 1.28, and it was 0.9. So we kind of knew going in, if you look back on that previous page, that it should have been around that area. So the Z sub 0, that Z score, is about I'll go with the particular, 1.282.
So for these ones, it's gonna be equal, but the other ones is about.
Right.
Okay.
Yeah. Now for number 2, and this will be the last one we do for tonight because I'm mindful of the clock, even though I let everybody go 40 minutes early on a daily basis. So the Z-score that represents Q3 is the callback. Q3 is also known as the 75th percentile. That's right back to box plots in Unit 1. All right. And the reason I mention this is because let's say you needed to figure out your 5-number summary from a distribution, but you don't actually have the distribution, but you know it's normally distributed. You could figure out what the first quartile is, the third quartile. The max and min should be easy enough, right? The median, and I neglected to mention this, is, now that I'm talking about box plots and things like that, the median, which is a really important part of a box plot, in a normal distribution, the median and the mean are at the same location, right? So if the distribution is normal, the mean is equal to 0, population mean, but so is the population median, right? So we could actually figure out our 5-number summary just by using inverse norm processes to come up with those benchmarks. Now, it's one of those things where it's kind of like a no need to reinvent the wheel. Like, now that I know that 90% to the left corresponds to 1.282, don't get me wrong, I'm not going to sit here and memorize these values, but they tend to come up over and over again. And so you will remember numbers before it's all over, like 2.575 or 1.96 or 1.645. Those values in a normal curve, they come up so often that it's kind of like for example, that radical 2 is equal to 1.414. maybe you're thinking to yourself, well, I don't know that. But if you worked with radicals often enough, radical 2 comes up very, very frequently. And when you go to decimal form, you see it like the 30th time you've seen it, you're like, okay, radical 2 is 1.4-ish. All right. So that it's along those lines. You'll see these numbers fairly frequently. Now, I don't know where I should put my z sub 0, but I do know it should be to the left of where I put it here, just for consistency. Although I won't be comparing your answers across problems when I'm grading a test. I look at each question as its own problem. So, don't lose too much sleep over, oh my God, I put it in the wrong spot. Because the reality is, you could do all the math, figure out where the z-score is supposed to be, and then draw the graph after the fact. So it really doesn't amount to much beyond that. This is my z sub 0. I'm looking for the probability that z being less than z sub 0 is equal to 0.75. Ish. All right, they say Q3, so it's definitely 0.75. But for other questions, you don't know. I mean, when they say 90%, do they mean 89.9%? Who knows? All right. So inverse norm, it's actually going to be the same exact function with similar parameters. Inverse norm 0.7501. Right? Because the mean and standard deviation are 0 and 1, and then, that's really all there is to it. Pop it in. And you get about 0.674. All right. So if I did know that there was a population mean or standard deviation that was other than 0 or 1, there's a couple ways I can handle it. But what I could do is use a z-score formula to convert this z-score 0.671 over to a real value. So if I know, for example, that on the last test, the mean was an 80 and the standard deviation was 10, I could figure out what score this would be on that scale corresponding with the 75th percentile or the 90th percentile or 95th percentile. I could do all that. All right. So that's kind of where this is heading. And you'll see as you go forward that, there's word problems associated with it. I mean, the next one is actually a word problem, but it's really these fundamental skills that are the driving force behind everything that follows. So take some time and make sure you're comfortable with this. Going forward, we're off next week. So it's Thanksgiving, so there's no class. We'll meet again the following week, right? And we're coming close to the end of the semester. So we got another test. We got the final exam. But I did ask you last week to read through this stuff starting on page 56. It doesn't seem to fit at all with what we're doing right now. But when we start talking about hypothesis testing, it will all come together. All right. So it goes back to what I said before. You got to kind of trust that there's a plan in place. For now, it may not feel like it, but it will. All right. And so that's